Hi, I'm Miss Hearn. Let's get started. We're going to talk about integration by part. Integration by parts is just a technique for integrating products where regular U substitution won't work. For example, if you look here in this first integral, x natural log of x dx, what could we let U equal? Well, really the only option would be the natural log of x, and the derivative of that would be 1 over x dx, not x dx, and so we'd be stuck. So we're going to look at another possibility, which is based on the product rule. You might recall that the product rule says that the derivative of a product of two functions u times v is u times the derivative of v plus v times the derivative of u. So we're going to integrate both sides of this equation with respect to x, and when we do that, we see that we get just uv on the left. On the right, we have the integral of u dv dx with respect to x plus the integral of v du dx with respect to x. Or in other words, u times v is the integral of u dv plus the integral of v du. All we have to do is rearrange that to get this theorem that we call integration by parts. We have the integral of u dv equals u times v minus the integral of v du. You can think of it as a kind of a double substitution. So let's try and find x, the integral of x e to the x dx, by applying this formula. The key to applying this formula is to make it fit the form integral of u dv. So you have to pick a u and a dv part of the formula. We have lots of possibilities. dv always has to have dx in it, but we can rearrange the integral any way we see fit. So what should we be looking for when we're choosing our u and our dv so that the formula results in something useful? When you're choosing u and dv, you want dv to be the most complicated part of the integral that is still integrable, meaning there's still a formula where you can integrate, and we want it to include dx. U is going to be whatever's left over. So another alternative is to focus on u first and try to find a part of the integral that if you took the derivative of that part, it would become simpler than it originally was. Then dv would be the leftovers. What I mean by simpler is, for example, if in your original integral you have an x cubed and you pick u to be that, notice that du would be 3x squared, which is slightly simpler than x cubed because it's a lower degree. So back to the list of options we had for finding the integral of x e to the x dx, we can probably decide to use the first option because we want the derivative of u to be simpler than u itself. If u is equal to x, then we know that du would just be 1 dx. 1 is simpler than the original function x. And then the dv, we want to be the most complicated portion of the integral possible that we can still integrate. E to the x is more complicated than just x, and we can still integrate it. So once we've chosen our dv and our u, the next step is always to find our v and our du. So for dv equals e to the x dx, v is going to be the integral of that. So that's going to be just e to the x. And for u equals x, du is going to just be dx. These are the things that we need to plug into our formula. So let's apply the formula. Integral of u dv equals u times v minus the integral of v du, which in this case means, remember, u we picked to just be x, dv we decided was all the rest of this stuff here, e to the x dx. And so we can plug in u is x, v we found to be e to the x, minus v is e to the x, and du is just dx. So we've substituted in, and now the next step is just to integrate the remaining portion that hasn't been integrated. And the integral of e to the x is just e to the x. So we have x e to the x minus e to the x plus c, and we're done. To check this, you can always just take the derivative. Remember, to take the derivative of x e to the x requires the product rule. And then simplify, and you'll see that you do in fact get back x e to the x, the original integrand. In our textbook, They give you some examples of some forms that come up and the u's and dv's that you can choose for those forms. So this is a nice little reference, so check that out. Here's an example from the WebAssign homework from our textbook. In this first example, they are telling us what u and dv to use. This is not always the case. You will have to choose that, but as you get more experience, you'll know what types of choices will work. And again, follow those guidelines. You want u to be something that if you took the derivative, that it would get simpler, not more complicated. And you want dv to be as complicated as possible, but still be able to take the integral. So you can see here that with the choice of u being natural log of x, du would be 1 over x dx. And 1 over x is simpler than the transcendental function natural log of x. With dv being x to the 4th dx, we integrate to get v. So the integral of x to the 4th dx is going to be x to the 5th over 5. So we can find that without any trouble, and that's what we're looking for with dv. We know that the integral of u dv is equal to u times v minus the integral of v du. The original integral was natural log of x times x to the 4th dx. That's our u and our dv, although it was in a different order to begin with, it doesn't matter. So that means that we can rewrite this as u times v, so natural log of x times x to the 5th over 5, minus the integral of v, which again is v is x to the 5th over 5 times du, which is 1 over x dx. Let's simplify a little bit and then we'll integrate. So this is going to be, let's see, x, let's just write it as 1/5 x natural log of x, x to the 5th, 1/5 x to the 5th natural log of x minus, we'll have, I'm going to bring the 1/5 out front, 1/5 the integral of x to the 4th dx. Okay, now we're going to go ahead and integrate, carry this all along, 1/5 x to the 5th natural log of x minus 1/5 of x to the 5th over 5 plus c. All right, so another way of writing that would be 1/5 x to the 5th natural log of x minus 1/25 x to the 5th plus c. Now let's see, in WebAssign, the answer given was c plus 1/25 of x to the 5th times 5 natural log of x minus 1. This is actually equivalent to that. To see that, I'm going to rewrite 1/5 as 5/25, right, getting a common denominator, and I'm going to factor that 1/25 out, so we have 1/25. I'm also going to factor out the x to the 5th, and let's see what's left behind. The 5 and the natural log of x, and then here we took out the whole term, so minus 1 plus c. So our answer is the same, and it would be fine to leave it in either format. You have the power of integration by parts. It can be addicting, so sometimes we try to apply it to things that it doesn't really apply to. Let me give you an example of 2 exercises, and let's decide which of these requires integration by parts and which of these does not. So A will be the problem, the integral of x cubed cosine of 2x dx. And the other one, B, will be the integral of x times the cosine of x squared dx. Okay, so these are similar looking. They both have an algebraic function being multiplied by a trig function. All right, but if you notice, the one on the left, first of all, it fits one of the patterns that we discussed earlier, that integration by parts works for, x to the n cosine of ax dx. But even if you didn't recall that, if you tried to do just a regular u substitution, a common choice for u is the argument of the trig function. And if u is equal to 2x, then du is just 2dx, which doesn't have an x cubed in it, so we're stuck. Okay, so this first problem does require integration by parts. Problem B. What if we let u be the argument of this trig function, which is x squared, then du is 2x dx. And although we don't have a 2, that's okay. We have the x part, and we can always compensate because it would be the same as having 1/2 times 2. So in this case, we could actually integrate just using a regular u substitution. So just keep an eye on that because a regular u substitution is a nice tool. It hasn't gone away, but this is the one that would require integration by parts. I hope you found this video helpful. If you did, please remember to give it a thumbs up, and that will help other students to find the video.